There were a few things that we could cross out. The reason that we are crossing these things out is that that's material that we have skipped. This is Nernst potential, this is equilibrium potential, or Nernst equation, equilibrium potentials. It's just stuff that you don't have to know. All right, but obviously everything that we went over on that Wednesday that wasn't including that is something that you have to know. So please do. All right? And again, let's make sure we understand what this is. That's just a change in membrane potential that's happening really, really fast. That's all it is. That is measured membrane potential. We start out at resting, then we hit, well, you tell me, threshold. When we hit threshold, we get our action potential. And an action potential is, once again, fast changes in membrane potential. How do those fast changes occur? Voltage-gated channels. Okay, voltage-gated channels are really, really fast. They move lots and lots of ions. We can see it because we see the big, huge changes in membrane potential. We know lots of ions are being moved. We know that the permeability of sodium is sky high here. We know that the permeability of potassium is high here. Okay, because we went over that stuff in detail. We saw the animation, and that's how we ended the lecture on Wednesday. We ended with the animation showing this. Now, we're going to skip some more stuff for right now. Hopefully we have time to come back to it. But the refractory period is something that I'm going to skip for now. If we have time to go back to it, we will. If not, it's not going to kill us if we don't understand exactly what it is. All right? So refractory period, both absolute and relative, for right now, we're not going to cover it. We might not. If I don't get back to it, I promise you that it will not be on the exam. I promise. All right? So let's move on from that. And let's talk about, well, look what else. Look how nice look how easy this exam's getting. The exam's getting easier and easier as I talk. That's out too. Maximum frequency of action potentials is out. Okay, I don't think it adds a whole lot to the story. What will add a lot to the story is this. So these words right here, it's included in these words here. So this is the details of what I just outlined, and it's that picture. We're going to draw that from scratch. And as I do, or as we do, I should say, I'll explain what it is. All right? So, just to kind of give you the punchline already, these little lines are individual action potentials. Right? These lines, you know, are these action potentials, the ones that we drew. All right? And what we're seeing is that we go from left to right, we have more and more action potentials. We have a greater, what's called frequency. So we're going to talk about the frequency of action potentials. How many action potentials are produced per second? That's what frequency is. All right? Now, when it comes to the number of action potentials that are produced per second, it's related to the strength of the stimulus. What kind of stimulus? It depends on the neuron, or it depends on the cell that's generating the action potential. If we're talking about pain receptors, for example, pain is a stimulus. Pressure receptor, pressure is a stimulus. My voice is a stimulus. The reason you can hear my voice is because sound waves are causing action potentials in your brain. My voice, the sound waves, are the stimulus. So if I whisper, you can't hear my voice as well. Why? Because you're not generating as many action potentials in your brain. But as I raise my voice, I'm causing more action potentials in your brain. Why? Because that means the stimulus gets bigger. If I turn the lights on in this room, that's a bigger stimulus. All right? So, a stimulus can be a bazillion different things. Doesn't matter what it is, but as it gets bigger, you generate more action potentials. And is that our action potentials information? Yes. That's how things get interpreted in your brain, for example. You have all those different areas of your brain, correct? As I raise my voice, what part of your brain is receiving those action potentials that allows you to hear? Tell me what lobe. It starts with a T. Temporal lobe, correct? Isn't that the area of the brain where you have neurons that are receiving information from your ear, correct? What about if I turn the lights on really bright? What part of your brain is interpreting that? Occipital lobe. Right? What if I come up to you and punch you really hard? It hurts. What part of the brain is that? Okay, right? So those different parts of your brain are receiving this information and they are interpreting it. So you have that somatosensory area of your brain. You feel me punch you. You feel me stick you with a pin. You feel your hand on a file. Okay? So, let's go through that. Let's draw this picture. Let's make it completely clear as to what we're talking about. And let's talk about pain. So we'll do pain. That'll be our stimulus. Pain is the stimulus. So we're going to take a neuron in your brain, and we're going to have an electrode on that neuron. We're going to measure the membrane potential of that neuron that's responsible for you to feel pain. Just one little neuron. So let's draw our little graph. Membrane potential versus time. All right, this is VM, membrane potential. Again, we're measuring the membrane potential of just one single neuron. Let's say the axon of that neuron. And we're going to see what happens to action potential frequency as we vary pain, that stimulus. What's that? It's resting membrane potential, right? All cells in your body have a resting membrane potential. The neurons that are in the somatosensory area are no different. So we have a resting membrane potential at this particular point in time. Do we feel pain at this particular point in time? No, we do not. There is no stimulus to this particular neuron. How do we know? Because the membrane potential is at rest. The only time you will feel pain is if action potentials are being generated in this particular neuron. All right? So what we're going to do, I'm going to shorten that just a teeny bit. I'm going to put a little arrow here. I'm going to make it small. That arrow is going to indicate the stimulus. So we're going to have some, so I'm going to come up to you with a pin. And I'm going to poke you with this pin. And I'm going to do it gently though. But enough to where I'm still going to stimulate. Tell me what kind of receptors, please. Pain receptors, free nerve endings, right? We talked about this in the skin chapter. So free nerve endings, right? Pain receptors are free nerve endings. Those are going to get activated. I'm going to stimulate them. If I stimulate them, what happens to membrane potential? Does it get more positive or more negative? Positive, right? When you have a more positive membrane potential, when you depolarize, that means we stimulate. We talked about that, I said at least a half a dozen times last week. So we're going to stimulate those receptors. That's going to lead to stimulation of the neuron in the brain eventually. But not enough to reach what? Threshold. So are you going to feel pain? No, you will not. The stimulus wasn't big enough. So what that's called, what the stimulus is called, it's subthreshold. It's a stimulus that does not cause this particular cell to reach threshold. All right? Are we good? Now what I'm going to do is make the arrow a little bit bigger because the stimulus is going to get bigger. In this particular case, I'm going to stick you a little bit harder. It's really not going to hurt, but you'll feel something. And I'm just going to reach threshold and boom, I'm going to get one action potential. A stimulus that causes threshold to be reached where one and only one action potential is generated is called a threshold stimulus. So we'll write the word threshold. One action potential. One, I'm going to abbreviate action potential, AP. Just one and only one. And that's how you know it's a threshold stimulus. All right? Now, I'm going to start to get a little bit more mean. And I'm going to stick you a little harder. And so now, I don't know, how about 3? 3 in 1 second. And then, let's make that arrow a little bit bigger. Then I'm going to stick even harder. Let's go 5 with this one. 1, 2, 3, 4, 5 in a second. Are you feeling more pain? Yes, and the reason you're feeling more pain is because that neuron is generating more action potentials. The action potential frequency is being interpreted. All right? We're not going to give it a name though. We're not going to give those particular stimuli a name. We will in just a second. Now I'm going to come up to you and I'm going to stick you harder and make the arrow bigger till we get to a point to where that particular neuron generates the most action potentials it can in 1 second. We've reached what's called the maximum frequency. Why? Because this is what's called a maximum stimulus. A maximum stimulus is a stimulus that causes a particular neuron to reach maximal frequency. I'm just going to pick a number right out of the air. I'm just going to say 7. 2, 3, 4, 5, 6, 7. Okay, that could have been 50. It could have been 100. It could have been 22. It could have been 13. I just picked 7. At that particular point in time, you're going to feel the greatest amount of pain that you can feel. All right? You can only ask cells in your body to do so much. And this particular neuron can generate, at a maximum, 7 action potentials in 1 second. It cannot generate 8. And because it can't generate 8, you're not going to feel more pain than you would at 7. All right? So that's what's called the maximum frequency. But what if I came up to you and stuck you even harder? So I'll make the arrow really big. What if there was a supra above, a supra maximal stimulus? How many action potentials do you think we're going to generate in 1 second? 7, because we've already reached our maximum. Do you think you're going to feel more pain though? If I stuck you harder, are you going to feel more pain? You got a 50-50 chance. Say no, because that's the right answer. It doesn't matter how much bigger the stimulus is, you're not going to feel more pain. It doesn't matter how much louder the sound is, you're not going to hear it louder. It doesn't matter how much brighter the lights are, they're not going to look brighter, because you've reached a maximum. So at a supramaximal stimulus, you'll still, 1, 2, 3, 4, 5, 6, 7, you'll still be at a maximum frequency. So here, we are at a maximum frequency, action potential frequency, at both a maximum stimulus and a supramaximal stimulus. Now, we're going to label the other two. The other two are obviously not threshold because we are generating more than 1 action potential per second. They're obviously not maximal because we're less than what the maximum is. These two together are called submaximal. A submaximal stimulus is a stimulus that causes more than 1 action potential but less than the maximum. And we can write that. So a submaximal stimulus, more than one action potential, but less than the maximum. That, by definition, is a submaximal stimulus. And you live in a submaximal world, by the way. On a day-to-day basis, we live in a submaximal. My voice right now, whether I whisper or whether I yell, it's still submaximal. As you walk, as you talk, as you feel things, it's submaximal, for the most part. Can we get to a point to where we are at a maximal or a supramaximal stimulus? We can. But 99.9% of the time, that is not the case. If I come up and shake your hand, what you feel is submaximal. Okay? There are other cells in your body that can generate action potentials, like muscle cells. So if I want to pick up, I'm going to bring my sunglasses, I did that. Well, I'll pick this up. I need to generate a certain number of action potentials in order for me to pick this up. If I want to pick this water bottle up, it weighs, 100 times more than what this weighs. I have to generate more action potentials. Doesn't matter, regardless. Submaximal to pick this up, submaximal to pick this up. Okay? So again, you live in a submaximal world. Most everything that you do on a day-to-day basis, most everything you're exposed to on a day-to-day basis is submaximal. Threshold, you don't even know that's going on. Okay? Threshold stimuli, you don't even know they're there. Certainly you do with these, but rarely is this ever going to happen. All right? Doesn't mean that threshold doesn't happen, doesn't mean the subthreshold doesn't happen. This stuff's happening all the time. You just don't realize it. Okay? You are more conscious of submaximal stimuli. Okay? Because they're bigger. Are you with me? So again, submaximal is 99.9% of the time what's happening in your day-to-day life. It just is. Okay? Good? So what we just drew there is the picture that I showed you initially, this one right here. and it's all these words. So I defined all these words, and now we just discussed all those words, and you learn